Okay, there is no one. But I think we are only 3 students actually.
Oh,
3 students. I mean, if you check, yeah.
Wow.
So I think most of the students have already taken this
Mm.
first round. So this semester, I think there are only 3 students, and they're all postponing it for the next year.
Oh, wow.
Yeah, yeah, okay. But I was expecting one more of them. That's not. Yeah, okay, that's fine. And how do you work this out? It's not necessary because you're here and there's no one on the other side. But, still, it helps. Sound. So you go with Ken or Ken?
Kenny, I mean, really whatever.
Ken?
Yeah, Ken is fine.
What do you prefer over there?
Ken, I guess.
Ken.
Yeah, Ken's fine. Short and sweet.
Is this your first semester?
Yes, yeah. This is my first day.
Stick. Supposed to give us attachment. And the first homework, which we can delay looking at. So I'm Satish. And this is physics, which is 510 classical mechanics. And maybe and just putting it like that so that it gets recorded and people can use it later on also. So sometimes I keep looking on this computer for sorry. Okay. Information. At least last time, or all the since last time we are having this. Whenever this has happened, there are at least few students there, so it seems meaningful to look at the computer.
Mm.
But this is the first time that I'm having one student here and no one there. So yeah. Um, so this course is going to be basically an extension of Newtonian mechanics. That's how it's a simple way of looking at it. And before yeah, so let's first let me say simple things about the course itself. Broadly, 3 topics. We'll say a stationary action principle. That's a lot of probably new words, it basically is saying that we know that Newton's law plays a very important role in the whole of physics, if you want. That's how, in a sense, fundamental science began, where you have one equation explaining everything. But then you ask, is this the fundamental equation, or is there a connection with something else? And there is a slightly more universal approach, which is more popular as Lagrangian mechanics or Hamiltonian mechanics. So we will see how all that gets connected. And that's a overlying principle of a big area of fundamental physics. So we will see. And that's broadly called stationary action principle. What is stationary action principle? In very simple terms, the universe is trying to, or the nature is trying to minimize energy. Like when we look at it as Newtonian physics, we say force, we have an intuition of force. But it seems like it is easier to look at things around us as if the nature is just trying to minimize the energy. And force is a manifestation of the process. So when the system is trying to minimize its energy, it seems like there is an action of force, and we will see the connection between force and energy. So we want to see that more in deep. And since I say it's a minimization principle, remember the calculus that if there is any function as a function of x, if you have a function, and if you have a local minima here, or extrema, we should say this is a minimum and that's a maximum, there the slope locally becomes zero, right? That's a very one of the first things we learn about calculus, that slope represents a tangent, and if you have an extrema, that's a that should be minimum. And stationary action principle is basically that concept. That is something, basically energy is trying to be minimized. So you want to look for the system has a function. In this case, we will have to extend it to what is called a functional, and we try to minimize that. So basically this whole point, the basic principle is just that. But at a slightly more deeper level, you will see, we will define what is called functional derivative and so on. That's very broadly what stationary action principle is. The second is we'll do Kepler's laws. Again, this should be at least the information content of Kepler's law should be familiar to all of us. But we want to go a little more detail in it using stationary action principle if you want. That's a classic system. You can, and third will be special relativity. So that's the broad three concepts we will go through over the semester. And you can say each one should take about a month or so, but I've noticed that things get stretched here and there. It depends on how fast we can go. In principle, it should be 3 months, but then it gets extended to 4 months, and see how it goes. So that's as far as the contents go. About the course itself, the logistics or the systematics of the assessment part of it. Let's see. First of all, the mode of this course. So I will be doing the same thing exactly that I'm here. So I come to this classroom, give a lecture, but then this gets recorded. And at the same time, I'm connected to Zoom. So a student has the option to come through Zoom. So then I see you on the computer instead of this, or you come here. But this is a small class. I mean, as far as social distancing goes, we are reasonably good. But at the same time, have that choice. That's a point of, and I leave it to the student if they feel uncomfortable upcoming, can always do that. It's also okay if you don't attend and then catch up with that, but I would not encourage it. Like it's, at least to me, it's a nicer feeling if there are students here. Already there are only 2 students registered, and if there is no one, I'm only recording. It's a little more boring stuff. But if that's what it is, that is what it is. So that's about the mode. And yes, once it is recorded, how do you see it? It is available on YouTube, because I make a playlist out of this. So that brings us to the course web page. The first thing we can say is that there is a course web page for this course. And that is so earlier this was on the physics web server, but last semester the physics web server died. So I had to, we now have a new server, but it cannot be accessed from outside. So it kind of doesn't help if you have a web server which cannot be accessed from outside. But they're still working on it. But meanwhile, there's a private, that's my website. It does all the job needed for it. This 20. So this is the year, the first month, and then is SIU, and then the name of the course. So if you go in here, everything should be, you'll get some information there. What are the things you want to look for here? One is that there is this link for the YouTube playlist. So I make a playlist out of all these lectures so that you have one of the, currently it's empty, but the first one will be loaded probably sometime today. And then you can click on that, you have all the lectures. Again, each lecture comes out to be more than an hour. So I have, at least for me, it is not very convenient to go back and look at it. But I've noticed that students like to go to some particular part of the lecture and they really want to listen to it again. So use it as you find convenient. So that's the website. What else is there? So lectures. Yeah, let's, and then we can come to the assessment process. Yeah. And there is the link to this website is also available on D2L. So we will also use, there is one more website which is D2L. So this is password protected. Where is the D2L? I think it is my courses. My courses. Start SIU. So if you use your, you must have got a net ID and a password in D2L. So you use that to reach that. This is where all your grades will show up, and also where you will submit your homework and any submission that will be necessary for the course will be, we will use. So this will be, so this is for lectures, resources, or let's say first homework. That's what's more important. Lectures, homework, and resources, let's say. So you look, you do, for those things you use this. This will be used for grades and for submissions, homework. Usually it is just homework submissions. In fact, for graduate level courses, even homework submissions, I encourage it in the class, but since we have this online thing going on, I noticed that this is more convenient. this by homework, it also means you can say a quiz. If there is a quiz, like I'll talk about that more, and even exams, if it is a take-home exam or an online exam, then you submit it. Any kind of submission, you do it here. Grades and rest of it goes other places. Yeah. So, so that's about where to find how to get information about the course. There's a we can talk about books next. Now, I give lectures on a topic, and typically it is common that you go by chapter to chapter in a book for a course, and that is I think at this stage we take a small break from that. It will be from books. I'm not saying that it won't be from books, but I may not go chapter to chapter from one book. So, but these are standard concepts. You can use any book you want. And what I suggest, I will refer to 2-3 books, but feel free to use these days. Internet is a very big resource. It's the internet, or it's always nice at this stage to follow one book. That's also good, but it doesn't mean that the classroom will go from one section to the other. But you will see that there is a connection, but you will have to make the connection as a student. That will be the part of the requirement for the course, that you should be able to connect things that's available outside with the lecture. Probably a little bit more on it. So the most important, if you want to, like usually students ask, oh, I don't want to buy everything. I want to buy one book, then which is the book you want to buy? The most standard book, if you go by the number of universities in the world, let's say for classical mechanics, then at this stage, Goldstein turns out to be a popular book. So that's one book to invest on if you want to. And I noticed that there's a website called archive.org, and based on my understanding, from what I'm reading, apparently that's a valid website. You can download from there. You don't get copyright books there, but still be careful about what you're doing. And I checked and I found that an older edition of Goldstein is available there. I think newer edition are still in proper copyright, so the older editions are available, which is good enough. Like any edition is good enough. So that's the modern textbook that is popular for this course. But at classics, there are always certain classics in a subject, and there is Landau and Lifshitz. That's it. And this is a whole, if you're not familiar about this book, this is a whole series of books they have. So this is a Russian school for a graduate level, and Landau is a famous physicist. He's a Nobel laureate, and he had a set of students, probably students also got Nobel prizes. So that whole school became a very important place, and they started writing books, or whatever he gave lectures on, the students being very capable, they took notes, and this became a Landau and Lifshitz series. So this is so you have classical mechanics, quantum mechanics, electrodynamics, so almost the whole graduate level courses you have. So that's a good thing to watch for very respected textbooks. Many people follow it, so that's something to follow. And the one that we will use is, so since this is a whole series, you'll talk about which one, and this is called mechanics. There is also another one which is in the same series that's called classical theory of fields. Which is also good, but that's a little more advanced. So, so for example, when we come to, I listed 3 topics earlier. When it comes to special relativity, the second volume is, or it's not the second volume, this volume is better. Mechanics is, in the early stages, mechanics is better for the Lagrangian part. A very older, so this, if you want to think of it, this is in the last 40 years, Goldstein is popular. Landau is like last 80 years, 40 years. Like Landau was in 1930s, like when the quantum mechanics came up. That's where, and he died very young. He died in 1956, I suppose, or 50s somewhere. But then his students kept writing and bringing out new editions. So this is 1950s, and this is 1980s, if you want. And if you go even older, if you go 120 years back, the very popular book is by Arnold Sommerfeld. This is, I said, Landau is the German, Russian school. This is the German school. Again, like Landau, I think half of his students got Nobel Prizes, but it's also an interesting story in the sense he never got a Nobel Prize, but he did great work, very respected. Apparently, again, look it up, these are all internet information. Apparently, he was nominated more than 70 times for Nobel Prize, but it not have. Right? But that's gossip history kind of. Nice story. Again, he has a whole series of books, like you have the Landau series, you have the Sommerfeld series, which is a German version of still older version. And here, this is a stage where you start losing connection with the notations. If you look at the notations, current modern notation, these two will work perfectly fine. This might take a little effort. You might, like it is old traditional way of presentation. Equations might, instead of a gradient, they might write d by dx completely expressed out. Vectors have not become very standardized to use. So those kind of things. But still, you can make a lot of connections. It's not like Maxwell's time is when slightly gets harder to read, but this is after Maxwell, so it is still readable. And this is again, it is the mechanics. So this is again a series, and in that it is mechanics that we will use. Even though I do use this book a lot in the beginning, but I changed the notation. As I said, the notation is slightly different. So I take the concepts from there and do it in like very slightly different notation. I mean, it is mostly notation, not the ideas. And it's also a cheap book. So like since it's old, so it is relatively cheaper. Nothing is cheap. We will do a little bit of calculus of variations. So, or I say a little bit, I mean, the whole Lagrangian can be thought of as a problem in calculus of variations. And what is calculus of variation? I told that the stationary action principle and minimum extremum, when we generalize this to more variables, then you talk about calculus of variation. And it's a nice little concept, but often how to put it, a little more abstract in the sense. So I've noticed that students struggle with it, but the idea again, I keep stressing on that, it is the extremum principle. It's just a generalization of that to a function instead of a variable. So remember, we want to get an equation out of a stationary action principle. When we are talking about a function, it's just a number, right? At this value, that's there. Here we are going to do something and get an equation out of it. So it's a little more generalized version of that. So that leads that we need to build up some formalism there, and that's calculus of variation. And for that, again, Goldstein does a good job, and this is more modern version of it. And I have noticed that there's a book by Gelfand and Woman. Only the first chapter of that seems to do a good job. So that's one thing I'll recommend. Again, all this should be available in the library, and in our library these days, if it is not available, they will, due to this pandemic, they give you a scanned copy and send it to you. So look for it, and otherwise that is what is called loaning. You can interlibrary loans. It's very easy. If you don't find the book here, you just say that I want this book. Within about a week, less than a week, it reaches, and then they inform you. So those are features available. So use it. And again, most of this, at least chapter-wise, is available on the internet. So you can use it. But I do know that as a student, you want to use one particular book just so that you can get all the concepts clear using one notation. For that, I'll recommend Goldstein because it's a modern book, a modern presentation. And more than anything, I think it is universal all over the world. Like if you say, oh, I used Goldstein, everyone knows about it. For that matter, all this, at least the first three, everyone should know at least sort of classics. So that's about the textbook. And I should also say, so how do you, so when it comes to no standard textbook, how do you, as a student, how do you know what should I spend time on, right? So that could be a confusion. So what I suggest is that you start with the lecture. So I present a lecture in the classroom, and that is a homework given to you. If you're able to work on the homework immediately, like you read the homework and you perfectly know, oh, this is what is going on, this is what is being asked, and you are able to attempt on it, and you might be able to, you might get stuck in between, but if you have enough hints on how to proceed, that means you're doing, I would say, very good in the classroom, right? That means you're getting enough ideas to proceed. But often what happens is that you've attended the lecture, you open the homework, and there is no idea of what's going on. It doesn't make sense with the lecture. It's not clear at all. And that's where you have to start reading the books. Right? You have to start reading the books so that you can make sense of the homework. And so in that process, you will start doing examples in these textbooks. By examples, in introductory level physics, it's common to say that we study something and that is the right example. But in an advanced stage, each section is an example. Each chapter sometimes is an example because these are long problem, like Kepler problem. Kepler problem, we do it in a month here. That's one problem in principle, right? A planet and a sun, we're talking about that. And so in principle, that's one problem. So similarly, each chapter of a textbook in principle is an idea. And sometimes what I do is that so for example, I go to Sommerfeld and I take a section and I make a homework out of it. It might be solved in this book. So then you make homework out of this, and it is written in as 5 problems. So that's how I make my homework. And you're allowed to use the internet. You're allowed to use, you're allowed to talk to, if in this classroom you have only one, but if you have peers, you're allowed to discuss your homework with each other, even look into each other's work. That's perfectly fine. But do your work, like write down your work. Don't photocopy something. I'm not experienced it, so I encourage discussions. That's the point. And even the internet, go and look for the homework. Even cutting and pasting, everything is fine. As I said, these are part of a textbook. Like the problems that I give are part of a textbook. It's just I'm making you read one section in my way. So that's what is that. And that's what homework is. You're learning stuff. But when it comes to an exam, there will be a new problem, and you should have enough hints for that. So that's where I say, when you're looking around, don't blindly look around. Have some thought process. Oh, this is what is going on. So do your homework in such a way that when there is something new, you learn from here and you're able to apply. And that's where the textbooks comes in. That's where the internet comes in. Internet resources come in. And there's plenty of resource out there. The only challenge is that these days there are so many of them. It's not a continuous process. So it's all scattered everywhere. But that's part of the learning process, that we learn to process the information out there. So does that help roughly how to proceed as far as homework and lectures go? Okay. So once you have, that brings us to the breakdown of, so I have to do some assessment also for the course. This homework is one piece of, there's lectures. Oh yeah, so one can say, let's begin with lectures, right? During lectures, I will spontaneously, like I don't come prepared with what I want to ask during a lecture, but often what happens is that when there is a lecture going on, either because students get ask me or I ask a question, and based on the interaction, sometimes I ask a question that the student has to explore. Right? Since it is not a well thought over question, the question itself might be wrong, right? Or it might be, usually it is not wrong. What happens is that it might be too hard to answer. You could spend, it could be or it could be meaningless sometimes, or so you can, mostly what happens is that it is too hard, that you cannot address it in a page or something. But the idea is that I want you to go and look for it, and don't spend too much time. Since the question is not well phrased, think of the question, whatever is going on, look it up, and give a maybe quarter page answer to that. That's all. I mean, the idea is just to whether you have spent time on it. And that's what I will call quiz. Right? So that's 10%. And earlier, when there was this regular semester going on, I used to keep it as once in a while I will ask this question and students answer. But since the online thing has come up, so on this D2L, I have to make a room for that. So for every lecture, there is one. So at least last semester, what I did was that during every lecture, there was a quiz, sometimes more than one questions. And I don't know whether it was okay or not. So, but the way I'm using it is that, see, my job here is, a part of my job is to assess you. So in that assessment, sincerity plays a small role. One is, of course, understanding the subject. That's the main thing. But sincerity in the sense, how often do you go back and think about it and you prove that to me? So this is a simple way of saying that how much do you, outside the classroom, how much do you do work for the course? And it's again where you don't spend more than 10 minutes. Even if you say that I thought about it, write a question and I couldn't get to it, but I gave it some thought. That's also good enough. That means that even if you put few minutes into it. So as I'm saying, it is not the content of the answer or the correctness of the answer is not the important point here. The point is that have you on a regular basis, have you submitted something for the course? And this plays a role here. So let me call this Y here, and we'll come back to this. Okay, so that's quiz. Homework is another big part. So that's 30% of the course. So you do the homework, submit it, and I grade it. Again, I'm usually lenient in grading, but this is important. Like by the end of this, typically there are about 10 homeworks in a semester. So each one is about 3%. That plays an important role. Start on the homework early. It is not a one evening process, as you will notice. It is not a one evening homework. So usually there is a week for it. So start early. If you start early, you get to know where you're stuck early, and you can come to me. You can, of course, go to the whole internet out there, and that's what I recommend. You should use the resources, textbook, internet, and so on. But if you're not able to get something, come to me, right, during the office hours or anything, and I will give enough hints that you should be able to go ahead. But don't lose points here. That's what I'm saying. That is midterm exams. There are 2 of them. So 15 into 2, so 2 times 15, so that's 30% there. And there is a final exam. So these are exams. Again, exams are pretty much like homework, except that you don't have the access to your resources. That's the only difference. So due to that reason, often exams are easier. I have also tried making exams like homework. It depends on how much response I get. Like if everyone is very regular in submitting the homeworks, I see that students are really learning from the homework, like they're really going and using resources. Then I use midterm and final exam also like homework. So basically, one homework is considered as a midterm. So not one homework. I design the exam exactly like a homework. You take it home. But sometimes what happens is that even if it is just one student in the classroom, so you have 10 students, and there's only one student who seems to be not doing the homework at all, and it's not very clear how much time and effort you put in. So then I have to assess them. Right? So then I have to put a question in a classroom. So that's the reason for this, but at least sometimes once in 1 and 2 times I'm able to assess, make the mid exams also at home. So that should be ideal. Now, based on all this, usually since the homeworks are harder, it's harder to score. There is also what is called curving. So what I do is, so after all this, let us say that you get 70 points, let's say. So you get 70 out of 100. So let's call this as X. So that's your X. So that's a score you received in the course. But then what I do is I define a new parameter here. So X prime is equal to X plus. Now, if I give you return back everything that you have lost, 100 minus X, then everyone gets 100 points, right? So that's meaningless. So what I do is I give you a partial of this. So whatever you've lost, I will give you, let's say, 20% of it. That's 0.20, like 20% of. So that's a possibility. And that's a way to increase your grade. So for example, if it is 70, you lose 30 points. So 20% of 30, so I give you back 6 points. So it becomes 76. So that's one way of curving. But I add a small feature to this. What I do is, based on the quiz, so remember quiz was very simple, right? I mean, I ask a question and you only have to go and explore it. I convert that in between 1 and 0. So if you submitted every quiz that I asked, then you get a 1 out of it. If you got half of the questions, half of the submissions, usually remember there is no correctness. If you submit it, most of you will get the points. So if you submitted everything, it's 1. If you submitted half of them, it's 0. So now I want to show this up here. So I multiply this with y. So for example, if y was 1, then you get all of the 20%. But if you got only 50% of this, you are eligible only for half of what I gave you. So that's a way of looking. And this also, I noticed that it seems to be a reasonable measure of how much student has participated in the course from their side. As far as sincerity goes, not the content ones. Okay, so that's what it is. I guess that should give a reasonable idea of what it's going to be. There are 2 midterms. The exam dates are already there. So to collect things together. So what is due at this point? That is homework 1. Okay, so that's due next. So I teach for 2, so it's next week, right? So it's 26th. So it's due on January 26th, which is a Tuesday. And I made it due right before the class. Right? I've noticed that sometimes students like it by the end of the day. I'm very flexible here. I think this is too early to use the flexibility, but if everyone in the class comes to me and says that we couldn't, as a class, if you come and say that, oh, we couldn't do the homework, please postpone it, I don't mind postponing it. I'm pretty flexible with the dates, but it doesn't mean that the course will get delayed. I might delay this homework, but the next homework will still come in. So this keeps going on. But the one I can shift it a little bit. Here it is, we have only 2 students. So if I would say one is half of you. So half of the class decides that, oh, I'm struggling, I did try. And if I feel that, yeah, that is going to help the student, that's perfectly fine. So don't hesitate to ask me for extensions. But at the same time, don't make it a habit. Every homework is getting done. I won't like it. And eventually I'll come down and say that, no, this doesn't seem to be working. But if it is useful, go ahead and if it's helping you. If you think that one more day is going to help, sure. That's okay. So that's homework 1. And then like the exam is the next one. So this is midterm exam. So the first midterm exam is relatively far. We don't have to worry at this point. It's all the way back on March 2. And if there is a quiz, we should. So what's a quiz I can make? You cannot make anything out of this. Yeah, here the quiz. Yeah. So this is how a quiz would be, right? So quiz for today. Earlier I used to call it extra credit. Now I give 10% to this. Earlier it used to be only Y. So I used to call it extra credit. But then it was last semester one of the students complained that there is no meaning to call it extra credit if you're giving 10% of your grade depends on that. So I said, okay, that's a good point. So I started calling it quiz this time. So yeah. So let's say, look up what is brachistochrome. So like, look up Wikipedia article on it. So that's it. This was the first problem that used the idea of calculus of variation. So the first problem that used the idea of calculus of variation. So this is how a quiz would be. So I'll give something, and now I can explain that. But then instead I use this feature of quiz for you to go and explore that. And look up the history. So that there's Bernoulli involved. Then Newton, so who solved this problem for the first time. Like he posed it, and of course he had solved it himself, and then Newton also solved it simultaneously. So that's a classic problem. Maybe yes, this a little better. So let's say you have so you have an incline, let's say. So there's 2 points here, and that is gravity pointing downwards. And and that's an incline. Right. And if we know that if we start a mass, let's say this is frictionless, a point object. If you want, you can make it roll also, but let's say this is frictionless surface, so the rolling is not important. It won't roll, right? If it is frictionless, so it's just sliding down. You can think of a bead, so you have a wire here, and there is a bead attached to this, and if it is frictionless, it will follow. And we know how we can calculate how much time it will take for this to go down. Now, one can try to argue, right? What will happen if you were to go down here like this and then reach it? And then again ask the same question, that how much time will it take for this? So this is, let's say, 1, and that's 2. And one could argue that this is a shorter path, right? So, time is equal to distance over velocity, right? And for each segment of that path, there is distance over velocity. Overall distance is small for the first path, so time should be small. But one might also argue that, oh, in the second one, in the early part of the segment, its velocity is really high. So higher velocity also means that there's a smaller time, right? So there is a give and take there. And so for example, you can go, obviously 2 cannot be the better one, because you can then go further down, right? So you can go make it an infinitely steep well, and you know that it will keep going down and it will take up. So that's going to be taking a long time. So probably 3 is probably not the better one. But between 1 and 3, there is somewhere, it's probably not even 1, right? Because this seems to give you a better one. So there's somewhere in between, there is a path, or there is a shape that will give you the fastest time. Right? Now the question is, what is that path? Right? That's a classic example of a calculus of variation problem. It is a minimization problem, but the solution here is a function. Right? We typically say in a calculus of variation problem, we have f of x, right? And that is an x, right? But now what? So this is the extremum problem. But now what we are saying is that out of all functions, so this is a very qualitative way of writing. You don't usually write the x here. So there is another quantity here. So let's say some physical quantity. Let me say capital F, and out of all functions, by function I mean all these paths, right, which is each path is described by a function. Out of all these functions, which one minimizes something? Here in this case, it's a time. Right? In this case, you're saying which one is the minimum time. Right? So which one minimizes the time? And again, the idea will be the same, that we have to take a derivative, but then this is a derivative with respect to a function. You change the function a little bit, what happens? And we want to build a formalism to address it. This is what actually is transfer control, but look it up and summarize this a little in the quiz. So that's how, so sometimes I talk so much on a quiz, but this kind of problems is what a quiz is about. And this is also a part of like understanding this problem should help you in the first month of the course, like a stationary action principle. This was the first problem in that context. So that should be in mind. And it's everyone has written about it. Ghostin has a section on it. Each of the books has a section on it. It's everywhere. So look it up. Okay, so we're about 20 minutes. Let's see, check it out. Yeah. Thanks. So let's do some things for the course. So let's review the Newtonian principles. So this let's see what Newton's laws is about. Newton's laws of motion. Newton also has the Newton's law of gravitation. That's also there. So let's see what is it talking about. So what is Newton's law? So, want to say something, Ken? So Newton's law, how would you say Newton's law? Say anything about it? Yeah.
With every reaction, there's an equal opposite reaction.
Yes, that's correct. Yeah, that will be Newton's third law, right?
Third law.
Yes, and anything else? How about, let's begin with first law. You don't know how to phrase it exactly, but what it means, sort of. First or second law. As an equation.
F equals ma.
Yeah, perfect. Yeah.
Obviously.
Yeah, that's let's say F equal to ma, right? So let's. I just want a context so that we can begin. Yeah. Perfect. Yeah. And is it okay if I ask questions like this? That's perfectly fine. The only catch is that this gets recorded,
Oh, that's fine.
so it will be there for your life to look at it. But yeah, I also make mistakes. So if it's since we are such a small group, so that's it might be a little more engaging in that sense. But feel free to say no or anything like that. It's a friendly atmosphere. I'm not really bothering. Yeah. Okay. So let's see. So what are we talking? Yes, F equal to ma is what? So that is. Let me write it down here. So that's F equal to ma. Right? So there's force, acceleration, and yeah. Let me write it as an equation. So yeah. So what is Newton's laws of motion? There are three laws, but the primary equation in them is that mass. So we talk about a system, so mass is sort of a system, but we also want to think of it as inertia, right? So it's mass times acceleration. What is acceleration? I have defined these things, and it's equal to the vector sum of all these forces that's acting on the mass m. Right? So a lot of information content in there. If you want to look at it, so this is motion, like accelerate. When we say description of motion, equations of motion, so we describe motion using acceleration, and then the question comes, why not velocity? Right? Why do we use acceleration to describe motion? Why not velocity? And that's where the first law comes in. First law says that velocity is not really important concept in the sense it's a change in velocity that is describing motion. Like if you're going with constant velocity, that's pretty much like you're at rest, right? Because you could be sitting on that particle itself and then you're at rest. So that's a reference frame idea. And we'll try to make this a little more precise. This helps motion. So forces, right? They help motion. So you exert more force, there will be more acceleration. So that's forces, and mass is it resists motion. So it's inertia, right? So inertia is a word that says it resists motion. But that is going too far ahead in the sense we haven't defined many things here. And it turns out that most of what we do in Newton's law, often we don't define in a very precise manner. So if we go back, first thing that comes in here is there is a time. Usually you say this is time t. And there is position, which is, let's say, r. So time, position, and this is position of m, right? Of mass m. Notice the moment I wrote these things, there are three concepts that came in, and often this is not very precisely defined. Position and time is still reasonable, but even that, as we saw in the later when Einstein came up, and these things do matter. How do you define them? And we don't really actually define them. Like when we say time, that is any monotonic function that is increasing is what time is. What is is there any difference between time and position? Maybe that could be a hard question, but still. Can you think of any difference between time and position? It's a hard question. But then, like one thing, again, it's not very important in this course, but as a whole, when you think of it as what we are trying to understand in the nature is that if we were, so position, the way to represent it is that if it is a one-dimensional, let's say usually you use the word letter X for it. So you have a description, right? And this need not be linear. Any function of X is also a position, but this is 0, 1, 2, and that's -1, -2, right? So, and if you're really talking about the position of a mass, you can go this way and then come back. So the mass in time actually evolves, its position evolves in time. But notice that its position could be 2, then it could be 1, then again 3, like it could keep changing. But time is one way. Time is monotonic. It doesn't have to start from 0, 1, 2. Whatever it is, you cannot go back in time. And that's apparently a significant difference. And it gets related, again, it is not related to what we are doing in this course, but this gets related to what is called entropy, right? And our current understanding is that our whole universe, or any system for that matter, tries to increase energy, sorry, decrease energy. So energy is, try to decrease that, and entropy, you try to increase. That means to say that if you let the system choose, if it had a choice, then it will actually increase the entropy and energy, and decrease the energy. And this entropy principle has to do with this, you often call it the arrow of time, in the sense that time cannot come back. But that's a very broad concept where we won't be able to get into the details in there. But what I wanted to point out here is that there are 3 concepts I have introduced, and I have not defined any of them. Like this is what our intuition tells us. There is a time that we talk about, there is a position of the mass we talk about, and the mass itself, m, what is it? It's a content, how much matter that is. It surely resists acceleration, but mass itself, we're just thinking of it as how heavy you are, like when we lift something, whatever intuition we have, that's all what is meant by mass. But with that feature, so 3 quantities in here, then comes definitions, then we have velocity. So velocity is defined as a derivative of change in position as a function of time. So that's a definition. Right? That's a clear definition. If we know these 2 concepts, we know that how r changes as a function of time, and so if you want, you can put in this velocity as a function of time. And acceleration is defined as change in velocity with respect to time. And the vectors just mean that the 3 coordinates representing the 3-dimensional space. So that's a definition. Again, force, it's intuition, right? We don't define what the force is. So F is a force, right? So these quantities of 1 and 3 remain sort of intuitive. We never sort of define what it is. The best we go at defining is that we say, oh, this is measured in using the units of newtons. This is measured in meters and so on. But precise definitions, that's a challenge. We don't know. And that then comes Newton's laws. And Newton tells us that mass times acceleration is equal to the vector sum of the forces. And from this point on, everything that you derive can be connected back to this relation. But these things are left open, right? So you can always come back and have, you can change things in that sense at a fundamental level if you want. So that's your Newtonian, I mean, this equation has everything in it, all the content of Newton's law. But this immediately tells us that if there are no forces, so that's mass times velocity or change in velocity, that's equal to 0. And that means that velocity is a constant. And notice that if the forces are not acting, even a particle that is, even a mass m that is moving with constant velocity is perfectly okay. Like there is not much significant difference between v equal to 0 and v equal to constant. And you might ask that, I mean, if you're down, like these are abstract questions, you can ask, imagine yourself to be in space, there is no reference point. We usually use stars as a reference point, and with respect to the stars, we seem to be moving, or it's easier to say that stars are moving with respect to us, right? And now you can ask at a very fundamental level, how do I ever know whether I am moving or the stars are moving? Who is moving among the 2? Like, and it's not easy to answer that unless you're accelerating. For example, the question you can ask is, this is again, I think it's a important feature. Sit. Yeah, how do you phrase this question? Yeah. Like we are going around the sun in circles, right? What's an experiment you can design which will actually confirm this? And I think you also want to say that actually, yeah, and actually that is sufficient. What is the experiment you could design that will prove, let us say, that will convince us all that you're actually going around the sun and it is not actually the sun that is going around us. So for example, if you have sun here, so make a lab. So there should be some, for example, if you make a pointer here, right, something that is going towards gravity, then this should probably change direction, right? Something that is sensitive to gravity, it should change direction. But can you design such a thing? And that's where it becomes profound that currently we cannot design such an experiment that measures the gravity of the sun, right? Because it is like saying, yeah, here is an example. So you're in an elevator and let's say the elevator cord snap and you're falling. Now, while you're falling, can you measure the gravitational force from Earth? So since you're falling, everything is falling. So there is no relative quantity in there, so you cannot measure it. And in that sense, now I'm not talking about, so that was Earth. So there's Earth and so there was an elevator coming down. But now I'm saying we want to sense sun. This circular motion or this elliptic motion, in that elliptic motion, each point of time you're actually falling. Like this whole Earth is just falling on the sun. It just turns out to be a particular orbit in which it keeps catching onto it while falling. It keeps doing this, keeps on falling forever, in a sense. And since that is happening, every instrument that you have in your lab that's also falling, so it cannot detect the presence of the sun. But then you can say that if you have two different things, there's a gradient out there, and that can be measured, but that's a very small measure. So, for example, tidal forces you might have heard, like due to the sun, the ocean water level on your beach keeps changing. Mostly that's affected by the moon. That's a primary component because the moon is closer, even though it's smaller, it plays a bigger role. But sun also has a contribution in it, and that you can use to measure that. Oh, that is you can measure the sun's gravity using that, but that's a very small feature, so it's a harder thing to measure. So yes, you can. The gradients come up. The change in gravity is easy to measure, but gravity itself is hard to measure. So those are those points tell you the essence of this. V is equal to a constant. Can you ever know whether you are moving or the other person is moving? So I'm sure in earlier courses that has been emphasized. So here, what we want to do is, we have lost a few minutes. Let me say what we could do is, three or four kinds of examples we will do. First case will be when force is a constant. So this is a constant. What's an example? A stone falling, when you drop a stone on the surface of Earth, gravitational force is a constant, 9.8. It changes very tiny bit, but mostly it is constant. When it is falling about 10 meters, it doesn't change much. So that's an example of that. That's a very classic. We have done that many times. We very quickly go about that. There's not much to it. The second is, what if it's a function of time alone, but not position? So by this, I mean that the force F is a function of time, but nothing else, right? A pure function of time. So we can do that as an example, one example from each. And then we can say the force is a function of position alone. So let's say position. What is a force that depends only on position and not on time? Can you think of such a force? Can you imagine a force that is only dependent on position? Gravity, right? G m1 m2 over r square, right? Yeah, right. So So that will be an example, and we try to do one day a simple version of that. Like it's kind of a review of what you're doing. And another is, let's say, this is dependent on velocity alone. Force depends only on velocity. So where do you see a force that depends on the velocity? Any thoughts? Like sometimes they talk about drag forces, like when you're driving your car, like how much drag you experience is that. That's an empirical law, and that's the example we will talk about. But a more classic example is the magnetic field. In a magnetic field, it's QV cross B, right? So it's that, and we will take that up later on when we're doing Lagrangian mechanics. We want to talk about that. So this is one way of doing very simply calculating, and there is a nice way of solving this Newtonian equation in each of these cases, especially this problem R3. That is a standard way of doing this. If it is only position dependent, you do 2 steps and you immediately get a relation that comes up, and we will do that. And but we'll take up that next class. The homework is not really connected to what I'm doing, but it's about a pendulum. But pendulum typically we approximate for small angle approximation, right? But that's not completely correct. So this is is there a possibility of doing this more correctly? The only thing that should bother you there is that I use what is called elliptic function. So this is basically let's say k of let's say x. So this is 0 pi by 2 theta 1 over 1 minus x squared sine squared theta. Now notice that when you have an integral, not all integrals are easily doable. So this is one of the integrals that when you do Kepler problem, it shows up, and it seems that it is not doable. Right? But then whenever you cannot do something, but you can evaluate this, right? You put in x equal to such a quantity, evaluate it. X equal to so much, evaluate it. That's how sine function is defined, if you want. Notice, like sine function is defined from some geometry. But what is useful is that we know so much about the sine function that there are so many properties, or it's a double angle formula thing. So there's a lot of addition formulas we can develop based on that. That's because we have studied it so much. This is not as much studied as sine functions, trigonometric functions, but still it is one of the most studied functions. So as far as you're concerned, this is just a function. Right? It has this representation instead of a trigonometric function defined in terms of geometry. This is defined in terms of an integral. Right? So when you're doing your homework, you will come across this, look this up, read a little bit, but as far as you're concerned, that's just a function. And I also ask you to plot it. There are standard softwares that can, so look up online Mathematica. Or use any feature you want. So when I ask you to plot something, use any plotting software, but since it involves an elliptic function, you want to use something that is I am familiar with this. Department computers have this on them, so you can use that. On the browser, you can get it. Online Mathematica is that. It's usually the first version. It's for using this elliptic function, it is free. But again, those are the places where, since you're starting something new, feel free to ask me. So it looks long, but it's pretty much a pendulum, like we're talking about a simple pendulum and information content. That's all. Yeah.